is our AP Chemistry lesson video for Chapter 11. This is Part 2, and I'm going to cover Section 11.3 through 11.5. So, we're going to talk about liquids a little bit. So, the resistance of a liquid to flow is called its viscosity. Oh, that should not say if, but it does. Oh well, typo on my part. It's called its viscosity. The greater the liquid's viscosity, the more slowly it flows. Viscosity is related to intermolecular forces and the likelihood of molecules to become entangled. So the more intermolecular forces the molecules have, the closer they want to be together. So they're going to flow slower and be higher viscosity. Viscosity increases with molar mass because we know intermolecular forces increase with molar mass. For any given substance, viscosity decreases with increasing temperature due to an increase in kinetic energy. That's why if you try to pour hot syrup, it'll flow a lot faster than cold syrup because those particles are moving faster. Surface tension is the energy required to increase the surface area of a liquid by a certain amount. The molecules in the interior of a liquid are attracted on all sides in all directions. So this is what an interior molecule would look like. So you can see it has intermolecular forces in every direction. The molecules on the surface have a net inward force. So see, there's nothing pulling this molecule upward. It's all pulling it towards the liquid itself. And so these forces affect what the meniscus will look like. So the surface tension of water is high because of its hydrogen bonding. The surface tension of mercury is even higher due to its metallic bonding. So mercury will bead up into almost a perfect sphere because of its high forces of attraction because of course, those metallic bonds it's made of. Okay, so that's intramolecular forces. Intermolecular forces that bind similar molecules together, such as hydrogen bonding and water, are called cohesive forces. Intermolecular forces that bind a substance to a surface are called adhesive forces. And so again, the balance of those two forces is what causes our meniscus to act a certain way. So, I know it might be kind of hard for you to see in the video, a wire's meniscus is like this, whereas mercury's meniscus is like this. Okay, I know it's probably hard to see in the video. So what's going on there? Why does one go like this, but yet one goes like this? Well, it's based on those adhesive and cohesive forces. So the meniscus of water is U-shaped because the adhesive forces between the water and the glass are greater than the cohesive forces between the water molecules. So when water is near the glass, it literally starts climbing up the sides of it. It likes the glass so much. The meniscus of mercury curves downward because the cohesive forces are greater than adhesive. So you can see that mercury is literally trying to pile up on itself. It's not even interested in touching that glass. So it forms a meniscus that looks like this. The rise of liquids up a very narrow tube is called capillary action. The more narrow the tube, the higher the liquid will rise, assuming that it has strong adhesive forces. And adhesive forces are responsible for capillary action. So, next we're going to talk phase changes. So hopefully you know all your phase changes. So solid to liquid is melting, or we'll call it fusion when we talk about delta H of fusion. Liquid to solid is freezing, but sometimes we'll call it solidification. Liquid to gas is vaporization, evaporation, or boiling, depending on temperature. Gas to liquid is condensation. Solid to gas is sublimation. Gas to solid is deposition. So, delta H values. So we discussed these in honors. Delta H of vaporization tend to be larger than delta H of fusion because in the transition from liquid to vapor state, the molecules must sever all intermolecular attractions. So if you look, here are some of my delta H of fusions, these short blue columns. Look at the delta H of vaporization. Remember, to go from solid to liquid, they just have to move out of their fixed positions. They aren't really moving away from each other that much. To go from a liquid to a gas, those molecules have to break those intermolecular forces. And then delta H of sublimation, delta H of sublimation equals the sum, I thought I spelled solidification wrong, equals the sum of delta H of fusion and vaporization. Because of course sublimation is directly from solid to gas, fusion is solid to liquid, vaporization is liquid to gas. And just keep in mind, delta H of solidification, that's where I thought I was headed with this, is the opposite of delta H of fusion in sign, same number but opposite in sign, and delta H of condensation is the opposite in sign of delta H of vaporization. Oh, well there we go, that's where I thought I was headed. And then of course delta H of sublimation is opposite in sign of delta H of deposition. So that if they're opposite processes, then they have the same value, but they're opposite in sign. So remember, we talked about our heating curve for water in honors. So here we have solid. Once you hit 0, it melts into a liquid. It stays at the same temperature during the melting process, and then it becomes a liquid, and we heat it, and then once it hits 100, it becomes a gas. It stays at the same temperature during the gas, and then we can heat it further. Remember, as long as you have a temperature change, you can use Q equals MC delta T. But once you're melting, you use delta H of fusion, and once you're boiling, you use delta H of vaporization. Because there's no temperature change. You can't use Q equals MC delta T there. Alright, so let's look at this one together. So it says, calculate the enthalpy change upon converting 1 mole of ice at negative 25 degrees Celsius to water, vapor, or steam at 125 degrees Celsius under a constant pressure of 1 atm. The specific heats of ice, water, and steam are 2.0 through, well, here they are, respectively. For water, delta H of fusion, that delta H of vaporization is this. Alright, so this is going to be a long heating curve problem. Okay, so first we need to go from negative 25 degrees Celsius to 0 degrees Celsius. So remember, on our heating curve, we're going to kind of work our way up our heating curve. So here, let me kind of draw our heating curve real quick. Alright, so we're starting at like negative 25 and we're going to 125. Alright, so this is going to be a 5-step process. Oh man, that's great. Okay, so remember, on these steps, I can use Q equals MC delta T. And on this, I use delta H of fusion, and on this, I use delta H of vaporization. Alright, so I'm going to start down here and use Q equals MC delta T. So they didn't give me my mass, but they said 1 mole of ice. Well, of course, we know ice is just water, H2O, and its molar mass is 18 grams per mole. Okay, so I'm going to plug in 18 grams for my mass times my specific heat. So they gave me 2.03 joules per gram Kelvin. Alright, and then they gave me temperature though in Celsius. See y'all, it doesn't matter. A difference in Celsius and a difference in Kelvin is the same. So what I like to do is just change this to degrees Celsius so that way I can see it cancel out. Alright, and so then for here I'm just going from negative 25 to 0. So 0 minus a negative 25 is 25 degrees Celsius. So my Celsius and grams cancel. So once I solve for this, I got 913.5 joules. Alright, next I need to hit this. This is delta H of fusion. So I start with my 1 mole of water. And then I multiply by my delta H of fusion, which is 6.01 kilojoules per mole. So my moles cancel, so I get 6.01 kilojoules. So here becomes our issue. We have joules and we have kilojoules. Okay, so we got to change one to the other. It doesn't matter which one you change. I'll just go from joules to kilojoules. So to do that, you move your decimal over 3 places to the left. So this becomes 0.914 kilojoules, like that. All right. So then I'll move on to here. So I have Q equals MC delta T that I can use again. So my mass again is going to be 18 grams. My specific heat for liquid water is 4.18 joules per gram, and like I said, I just changed my per Kelvin to degrees Celsius. And then when I'm at the liquid, I go from 0 to 100, so my temperature change is 100 degrees Celsius. And so for this one, I end up getting 7,524 joules, but I'm going to go ahead and change that to kilojoules, so it becomes 7.524 kilojoules. Alright, so next I can use my delta H of vaporization. So I, of course, start with 1 mole. Oop, that should say times. My molar heat of vaporization is 40.67 kilojoules per mole. So that's 40.67 kilojoules. Alright, and then the last step is I got to do this last little bit right over here. Whew, I'm running out of room. So I can use Q equals MC delta T again. So my mass, of course, is 18 grams. My specific heat for steam is 1.84. And it's joules per gram degrees Celsius. My temperature change, we're going from 100 to 125, so it's 25 degrees Celsius. So my grams and degrees Celsius cancel, and for that I got 828 joules, which of course I need to change to kilojoules, so it becomes 0.828 kilojoules. So then, the last step is I add up all of my kilojoule amounts. All right, and so, forgot this one. So once we add up all those kilojoule amounts, I got about 56 kilojoules. All right, and so that's the way you work your way up the heating curve. Now if you go down the heating curve, all of your numbers will be negative instead, because heat will be released instead of absorbed. All right, so hopefully you remember that from honors. All right, so there will be a practice question next, so of course, pause it and try it on your own. You know I always like you to do that. All right, so y'all are going from 100 grams of water at 50. So see, you don't have to go up the whole heating curve. You're starting about right here to ice at -30. Okay, so really you aren't doing this top part. So you're going this way. So you're going to go here, here, here. So you have a 3-stepper. Okay, so pause the video. Y'all try this one. You may need to pull your delta H values and your specific heat values from the previous slide, but I'll assume you've done that and we'll look at it together. So I'm going to start with Q equals MC delta T for this portion right here. All right, so we have 100 grams of water. So my mass is 100 grams. For water, we have 4.184 joules per grams degree Celsius. Here I'm going from 50 to 0. So 0 minus 50 is -50 degrees Celsius. So that's how my number is going to be negative for this one. So I got negative 20,000, oh, did I get 20? I can't even read my handwriting here. Yeah, it looks like 20,900 joules, which of course we need to change to kilojoules, so it's negative 20.9 kilojoules. All right, so then I do my delta H of fusion, but we are freezing it now. So I need to use delta H of solidification. So remember, I just take fusion and change it to negative. So I got to start with my grams, but remember, we need to get to moles. So 18 grams of water is 1 mole. Then I can use my fusion, which they told us is 6.01 kilojoules per mole. I didn't have to do this step on the last problem because they gave me moles. All right, so once I solved for that, I ended up getting, oh, and sorry, this is negative. Because of course we're cooling it, so we're actually using delta H of solidification. So I ended up getting negative 33.389 kilojoules. All right, and then last step is I need to go from here to here, so I can use Q equals MC delta T again. So my M is of course 100 grams again. My C is 2.03 joules per gram degree Celsius, and my temperature is going to be from 0 to -30. So -30 minus 0 is -30. So my Celsius and grams cancel, and for this one I got negative 6,090 joules, which of course ends up being negative 6.09 kilojoules. So I take all 3 of my kilojoules, whoops, sorry, there's a decimal right here, add them up, and I got about negative 60.4 kilojoules once I put them all together. All right, so hopefully you got that right. You're just working your way up or down the heating curve. It depends on if you're heating it or cooling it. It's all that matters. But remember, if you're heating it, all the numbers will be positive. If you're cooling it, all your numbers should be negative. All right, so supercooling. Supercooling is when we remove heat from a liquid and temporarily cool it below its freezing point without forming a solid. This occurs when the liquid is cooled so quickly that the molecules don't have enough time to get in their orderly structure. A supercooled liquid is obviously very unstable. Critical temperature and pressure. So we talked about this a little bit in honors when we talked about phase diagrams. So the highest temperature at which a distinct liquid phase can form is referred to as the critical temperature. The critical pressure is the pressure required to bring about liquefaction at this critical temperature. Above the critical temperature, the kinetic energy of the molecules is greater than the attractive forces that, oh, I put than and then. You know, I obviously couldn't pick between two. Attractive forces that lead to the liquid state regardless of how much the substance is compressed. So above your critical temperature, temperature, you cannot, with any type of pressure, make it become a liquid again. The greater the intermolecular forces, the greater the critical temperature. So 11.5, vapor pressure. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid or solid phase. So like if we have water in a flask and we put a lid on it, in the beginning, there's no water molecules here. But over time, some of them are going to evaporate, and that's going to cause a pressure for those water molecules. And since it's above its liquid, that's called vapor pressure. At any instant, some of the molecules on the surface of the liquid possess sufficient energy to overcome the attractive forces and escape to the gas phase. But eventually it'll reach equilibrium because this area will be saturated with the water molecules. So every time a new one vaporizes, one will condense, and that's when we get equilibrium. So the weaker the intermolecular forces, the larger the number of particles that can escape and the higher the vapor pressure. So substances with low intermolecular forces tend to have higher vapor pressures because their particles can more easily evaporate. If the container is closed, the rate of evaporation will eventually equal the rate of condensation and equilibrium will be reached. So that's what I told you just a second ago. Substances with high vapor pressure, such as gasoline, evaporate more quickly than substances with low vapor pressure. Liquids that evaporate quickly are said to be volatile. Vapor pressure increases with increasing temperature because, of course, as you increase temperature, more of the particles have that ability, that sufficient energy to evaporate. A liquid boils when its vapor pressure equals external pressure. So boiling point is when your vapor pressure equals external pressure. If your external pressure is 1 atm, which is our standard pressure, we call that the normal boiling point. As external pressure decreases, the boiling point decreases and vice versa. So let's look at this one. So we have a vapor pressure versus temperature chart here. Alright, so it says, use figure 11.24 to estimate the boiling point of diethyl ether under an external pressure of 0.8 atm. Well, they gave me 0.8 atm, but my pressure right here is in torr. Okay, so the first thing I did was, of course, change it to torr so I could figure out where I'm looking on my graph. So I have 0.8 atm, so I know 1 atm must go on bottom, and that equals 760 torr. So once I did that, I figured out, oh, that's 608 torr. So see, that's the problem. If you try to look at 0.8 way down here, you're going to pick something super low. All right, so we're at about 608 torr. So in other words, we're about right here, and we're talking about diethyl ether. So I come across right here, and I look at my boiling point, so we come down to about right here. So I picked that it was about 25. That's what I picked. Okay, so that's where you got to be careful, because if you had looked at 0.8 instead, you would have picked way down here. Okay, so you got to make sure your pressures align. So they gave me ATM, but on my graph it's torr. So you just got to make sure you have the same unit, as always. Oh, okay, well here I put about 30. Well, that's okay. When I was eyeballing it right there, it looked like about 25. All right, so y'all try this one. I'll assume you've done that, and then we will look at it together. So it says, at what external pressure will ethanol have a boiling point of 60 degrees Celsius? So I find ethanol. So here's ethanol. We want a boiling point of about 60. So I go up here, and then I just go across like this. So we're about right here. So I put about 330 torr, because of course my pressure on here is torr. Okay. So if you look, like 300 would be about right here. So I put about 330. We'll see if I put that on my PowerPoint. Oh, I did, about 330. All right. So most of what we just discussed still was from honors. We just kind of started pulling things from different units because we've done the heating curve for water. We've talked about critical temperature and pressure. We've talked about phase changes and things like that. So again, hopefully most of that was just a review.